look at something called biconditional statements and how they work with definitions. What I mean by that is, in order to work with a biconditional statement and definitions with them, we have to go backwards a little bit and define a couple other things real quick. So one of the things I need to define with you guys is a term called conjecture. Okay? So I want to go back and define what's called conjecture. Exactly, it's a guesstimate. It's an educated guess. A conjecture is coming up with some, obviously some really educated guess. Real world stuff, I would say, I think the ground is very dry. By looking outside and see lots of patches of dark grass, no green grass, a lot of dying grass. Seeing how the leaves are just kind of change color into it. Well, yeah, it is because we haven't had really any rain forever, so. Yeah. No, it's. I'm going to have an educated guess, like a conjecture, and say that's not a good idea. Your conjecture is not a smart one. So that doesn't make any sense. I apologize. Conjecture, you guys do this all the time. You're looking at certain situations, you're coming up with an idea. What you're doing is that you take conjectures and you base them off of certain situations. As a teacher, I do this all the time. I'm looking at when I'm showing you guys new material. If I'm getting the sideways or squints or looking up at the ceiling or trying to figure out if that makes any sense versus the nod and kind of like you nonchalantly just kind of you don't kind of hunch over and turn yourself inward. You kind of keep yourself positive. Like, all right, I see what's going on. You know, you kind of keep up with the idea. As a teacher, you kind of learn. I've never heard this before. The feel of the room. You ever heard anybody say that? How you can kind of sense how you sense your audience, whether or not they know that you're just kind of totally BSing them, or that you are actually making some semblance of sense. It's kind of that idea where you're taking in the observations around you to see if people are actually following along with what's going on. Teachers do it all the time. What you're using is something called, yes ma'am? We never go off topic. Yeah. We have them in the sense because what's this format on? Once again, I'm going to use some inductive reasoning at that last statement and say you weren't thinking. Let's all go stand back by here. Come on, let's go. Everybody up. Now, here's the thing. In the classroom, I don't believe that there's going to be a weight limit that we need to worry about, but there are fire codes as far as how many people can be in a room at the same time. You guys have all seen like the idea of a pool, no more than like 100 people can be in a pool at a time, certain capacities. In an elevator, you don't want to have more than, whatever it says, like 10, 12. Well, but you get in the idea of what you're looking at specific capacities. Classrooms aren't any different. Classrooms are supposed to hold X amount of space and per student get a certain amount of things. And there's so many variables put into the equation to figure out room capacity for a schoolroom versus room capacity of like a hotel. When they talk about classrooms, you really can't get the right formula from anybody. Nobody will tell you how they calculate it. That's kind of one of the reasons why we keep seeing more and more kids into a classroom. When you guys know Mr. Severino, right? Most of you guys probably do. Sev brought up a thing the other day that when he started teaching here 11 years ago, or 10 years ago, excuse me, 10 years ago, we had only about 1,400 kids. And I think we had 12 math teachers. 12 and a half math teachers at the time. One person was real short. What a half teacher is nearly taught like 3 classes. So we had 12 and a half math teachers 10 years ago with 1,400 kids. Now we have 2,000 kids and we have 10 and a half math teachers. So we have more students per teacher and less, and like all that. So back 6-7 years ago, our class sizes were about 26, 27 kids because we had more teachers. Now our classes are all, I mean, you guys all see it, they're all 35s. You know, I have a class of 36, 37. So that's what's kind of gone throughout because they can say, hey, we can just put another kid in here. But anyway, so inductive reasoning. Let's use some conjecture and inductive reasoning to come up with what they're implying with this statement.
I'm worried.
So who are they worried about? Like this animal? Do they care about you? No. Right. So they're more worried about the animals at the zoo than you and walking around it. So it's one of those silly little things that you see. You don't have to, I wasn't expecting you to write that down. Don't worry, I'm just showing you ideas. But what you want to do is to use these ideas of conjecture and inductive reasoning to come up with some statement and or diagram via this information. In the information given here, it says that you have points A, B, and C, and then you have lengths. AB is 10, BC is 8, AC is 5. Make some sort of a conjecture and possibly draw a diagram. Oh, are they still back there? All right. So in this case, you have points A, B, and C. What can you come up with that information? I'm hearing triangles. Am I saying line? Okay. All right. Well, let me show you both versions. So your conjecture is that they're making a line. I'm sorry, triangle. So we have points. So you're saying points A, B, and C make a line. All right, so the triangle. AB was 10, BC was 8, AC was 5. Okay. And then you were saying that they made a line. AB was 10, BC is 8, AC is 5. And that makes no sense, does it? So what's happening here is the original conjecture that Sam, right? Not Sam, that's your bro. No, is there a Sam yet? Cousin, yes. So it's Manuel. I was close. Sorry. So it was a family. I'm getting there. Come on. All right. So your idea that your conjecture that they created a line, what we did is we came up with a counterexample to show that it was false by drawing a diagram saying that this is an impossible possibility. But yet this can be can be. Okay. All right, you're using the idea of specific information given to you to determine whether or not something is feasible. Okay? Not too terrible, is it? Yeah. That's where we get the idea of what we were talking about yesterday, that counterexample. Counterexamples are extremely important in the sense that they can disprove conjectures. Okay? That's what they do. And it can be anything. It can be a statement, it can be a sentence, it can be a diagram like we just drew. All right? Counterexamples can be anything to disprove a statement. Okay? Not terrible? All right. Well, then let's talk about this idea of what's called a biconditional statement. I've always thought that a biconditional statement is always easier to talk about by showing how it's made. Because once you see how it's made, you're like, what's that? Sure. Anyway, so let's take the following statement. An angle is a cube when it measures less than 90 degrees. Nope. I'm going to make a biconditional statement. It's easier to show you what it means by making one, as opposed to just throwing the definition out. The definition kind of sucks. Showing how it works is easy. So this is that generic statement that we usually start with. Remember the past few days you've had this generic statement that it said, hey, write it as a conditional statement. The conditional statement was the if-then, P implies Q. All right? So an angle is acute when it measures less than 90 degrees. Is that true or false? All right, so we're starting with a true generic statement. Let's write that as a conditional, an if-then. So a conditional So I'm hearing it kind of sputtered about here. If I go to a conditional statement with a P and Q, it says if an angle is acute, then it measures less than 90. You're okay with that? All right. True or false? True. Remember, anytime you write down a conditional statement, a P implies Q, Q implies P, any of those, you always have to say whether it's true or false. And if it's false, you always have to give a reason. Yeah, reason, counterexample, either one of those is fine. Okay. Now, after the conditional, we say it backwards and it became the converse. So the converse of this is Q implies P. Remember, that just means you're switching the order. What would that look like? Okay. If the angle measures less than 90, then it is acute. Right. If an angle measures less than 90, then it is acute. Okay. What we're looking at here, guys, is that we're saying it forward. If an angle is acute, then it measures less than 90. We're saying it backwards. If an angle measures less than 90, then it is acute. Is that true or false for that one? True. Also true. So what happens here with a biconditional statement? A biconditional statement is when your P implies Q and Q implies P are both true. Because what you can do then, it means it works going both ways, where you have two conditions. Biconditional is where that comes from. it works out to be, we use the word if and only if. We'll start using this term. An angle is acute if and only if it measures less than 90. That's the straight definition of acute angle. An angle is acute if and only if it measures 90. If an angle measures less than 90, or if an angle measures less than 90, if and only if it is acute. Or excuse me, an angle measures less than 90 if and only if it's acute. But instead of writing out the words if and only if, because there's a lot of letters, we have an abbreviation. If stands for if and only if. Okay? If stands for if and only if. You want to write out the word if and only if? By all means, go for it. You want to write out if? Go for it. So the if statement would be an angle is acute if it measures less than 80 degrees. An angle is acute if it measures less than 90 degrees. You see this with just about every single geometry definition. It can be written as a biconditional statement. A triangle is a right triangle if and only if the Pythagorean theorem holds true. If the Pythagorean theorem holds true, if and only if it's a right triangle. Vertical angles are congruent if and only if their sides create opposite rays. Two angles are supplementary if and only if they measure less than 100, or if and only if they measure between 90 and 80 degrees. Okay? You get through those like that. So, Like I said, I'm going to take the 3 days of assignments. You're going to hand it all in on Friday. It's fine. Just let me pull it out this year. Just add to it. Whatever you want to do. Okay. All right. All right, go ahead and get started on that, and then we'll go on from there. Yes, ma'am. I just know sometimes it's easier to add to it. I know some people don't like